Wearable sensors for full-body motion capture enable seamless motion understanding. They allow continuous monitoring for user states and even open the door to communicating through body language with AI agents. The Inertial Measurement Unit, or IMU, is already embedded in many everyday devices and is a promising tool for motion capture. IMUs measure orientation and accelerations. The existing challenge is that can we reconstruct detailed full-body motion using only a very small number of IMU? That means reducing the number of sensors while maintaining detail is one of the critical challenges in this field. However, two key barriers exist. Orientation data from IMU is sparse, and acceleration mainly indicates when motion starts, rather than how it evolves. So this makes time dynamics crucial. An early error can easily snowball into larger mistakes as sequence continues. Instead of mapping IMU signals to poses in a purely deterministic way, therefore we adopt a probabilistic approach. At each time step, we represent motion as a distribution and refine the distribution over time. This allows the model to not only predict motions, but also to reason about uncertainty. To achieve this, we use the matrix Fisher distribution. A rotation matrix belonging to a special orthogonal group can be modeled with this distribution. The matrix Fisher distribution is designed for rotation and captures both the mean rotation and the uncertainty around it, which is the how tightly or loosely possible motion cluster around that mean. Here we face a challenge. So if the model tries to predict a very sharp, condensed distribution, training becomes unstable. In contrast, if the motion distribution is too broad, the accuracy is lost. So to address this, we address two different ideas, RU-Mamba and progressive distribution narrowing. So RU-Mamba explicitly separates the representation of rotation and uncertainty, making the model more robust. So each block predicts a normalized uncertainty value, which is then multiplied by a pre-assigned scaling factor and exponentially scaled. This restricts the model output range while enforcing the distribution narrowing across the blocks. The PDN further refines the process by gradually increasing the scaling factors across layers. Early layers keeps the distribution broad to allow multiple plausible poses to happen, while later layers progressively narrow it to achieve accuracy. Normally, models fail to condense distribution under large, exponentially scaling values, but with a normalizing uncertainty and assigned scaling, our model can maintain stability and precision. With 6IMU, our model achieves state-of-the-art performance on DIB test datasets. Even with only 5 sensors, it delivers compelling results compared to the previous models that required 6 sensors. Appalachian study below confirmed that removing PDN and removing RU-Mamba as uncertainty separations leads to significant performance drops, demonstrating the importance of both components. This design also produces interesting dynamics. So for motions with heavy lower body involvement, the model maintains higher lower body uncertainty in the final layers while concentrating more on upper body distribution. In contrast, to compensate that, earlier layer passes a wider distribution for the upper body, which means that the network learns to balance exploration and precision across time. So in practice, this allows us to capture highly detailed motions, daily activities, sitting motions, golf, or dancing and boxing, using 6 IMUs and even fewer. Remarkably, when we reduce the sensors to 5, 4, 3, or 2 sensors, the system still tracks fine-grained movement in real time. So compared to the prior state-of-the-art models, our approach remains robust even with fewer sensors, which highlights the powers of modeling uncertainty and handling reduced sensor count while maintaining the accuracy. So in summary, probabilistic modeling with RU-Mamba and PDN not only achieves state-of-the-art accuracy, but also makes motion capture practical with very few number of sensors. With the Mamba structures and efficient batch-wise distribution sampling, our model delivers strong real-time performance. It can capture detailed motion reliably with 6 IMUs, 5 and 4 IMUs, and with even 3 and 2 IMUs in real time.